Hello, I'm going to talk about the second part of why Gaussian elimination works. Okay, so this is part 2. In part 1, we talked about lemma 1, lemma 2, and now we're moving on to the third lemma, which is, hopefully you can see this, lemma 3, right here, right. Camera's acting weird. Let's try that. I think that gets you in there. Okay, lemma 3. Every elementary row operation is reversible, and every elementary matrix has an inverse. So again, that's there. Okay. Now let's talk about its proof over here. And yeah, sorry, there's the statement right there. Okay. So, all right. Silly, I didn't realize. Okay, so every elementary row operation is reversible. It is the same statement, just slightly rephrased. And every elementary matrix, EI, is invertible. To say a matrix is invertible is the same thing as to say another matrix called EI inverse exists. Okay? All right, so the row operations, switching rows I and J. How is that reversible? Well, just do it again. If you switch rows I and J, switch them again, and you'll get back to the original, right? So that's why the operation is reversible. Let's look at the elementary matrices. So for example, if you have E1 to 3 switched, right? So here it's first and third rows of the identity are switched. If you just multiply it by itself, look what you get. Multiplying this row by that matrix picks up that last row, but plops it right up here. Second row doesn't have any change. Third row goes through, ignores everything but that first row, but puts it in the third row. So this matrix times itself is equal to the identity. When you're trying to prove something has an inverse, you have to show that if you multiply them in one order or the other, you still get the identity. Well, this statement does that because these two are exactly the same. So therefore, the inverse of E13 is E13. And in general, I think you can agree that would make EIJ swap. Its inverse is just itself. Okay. Moving along. Let's see if you can see this. Yeah, okay, good. So the second row operation, multiplying a row I by an alpha not equal to 0. How do you undo that? By multiplying that same row I, but this time by 1 over alpha. Now that exists because alpha was always said to be non-zero. So 1 over alpha is a real number. So for example, E that has the row 2 multiplied by 5 looks like this. It's the elementary matrix. Its inverse is going to be E1/5 row 2, like this. Now I have to show that that's true, that if you multiply one by the other or in the other order, you still get the identity. And if you carry through this multiplication, you'll see that's the case. The fact that we have these, the first and third rows looking like they do, means that they're going to pick up exactly what's over there. They stay the same. In the second row, 0, 5, 0 comes through, ignores rows 1 and 3, and just multiplies everything in here by a 5. 5 times 1/5 gives you 1. Same thing if we do it in the other order. The 1/5 in the second row is here. When it comes through and multiplies through here, these two zeros have it ignore rows 1 and 3. It just multiplies everything in that row by 1/5, giving us the second row of the identity. So in either direction, their product gives you identity. That makes them inverses of each other. And in general, if you have an elementary matrix that multiplies row I by alpha, its inverse is going to be 1 over alpha, the elementary matrix with 1 over alpha multiplied by row I, that same row. Okay, so we're going along and we're proving that the row operations are reversible and that their elementary matrices are invertible. Let's come over here. The third row operation, always the most work, right? Adding alpha non-zero times row I and then taking that product and adding it to row J is a way of phrasing it, or more formally writing it this way. The new row J will be equal to itself without any multiples added to alpha times row I, where I is not equal to J, they have to be different rows, and alpha has to be non-zero. This also can be undone by repeating the same type of elementary row operation. Okay, so if we want to undo having added alpha row I, this is why this notation is kind of nice, you just got to now to that row J, subtract alpha times row I. For example, here's a 1, 2, 3. It's row equivalent to 1, 2, 3, 4, 5, 6, 12, 18, 24. By what row operation? New row 3 is equal to old row 3 plus 5 times row 1. Right? 5 times row 1 is 5, 10, 15. So if you added that to 1, 2, 3, yes, you would get 12, 18, 24. But that is row equivalent to 1, 2, 3, 4, 5, 6, 7, 8, 9. By the row operation that says we're going to turn this old row 3, now this is the old row 3, into a new row 3 by adding negative 5 times row 1 to it. So here's negative 5 times row 1, negative 5, negative 10, negative 15. If you added this to the 12, 18, 24, right, you would get back to 7, 8, 9. Notice that if I call the matrix, the elementary matrix, excuse me, not call, but the elementary matrix that does this row operation, if you remember, this one here would be denoted E1, 5, 3, and the one that does this row operation we'd call E1, negative 5, 3. So here they are, those elementary matrices. If you multiply them together, you'll notice the first two rows here being like the identity, just repeat exactly what's here. So that stays the same. Last row comes along, that 5 plus 0 plus 1 times the negative 5 gives you 5 minus 5, or good old 0 right there. And you'll notice multiplying that through here, the others, and the 5 gets ignored here, and that 1, 0 doesn't, and this 0 doesn't do anything to that row, and it just picks up the rest of this row. So we get 0, 0, 1 in that last row, the identity. And you can check yourself that if you switch this multiplication, you would also get the identity. So, in general, we're going to say that the third type of row operation, which is performed by using this elementary matrix, I alpha j. Again, what does that look like? Using this as a guideline, we're taking, let's see, yeah, to row 1. Okay, so this scalar got multiplied by that row, got added to this row. So this scalar alpha times that row I, that product added to j, is that elementary row operation in general. If you multiply it by a similar one, but replace the alpha with the opposite of alpha, you're going to get the identity. And if you take the multiplication in the opposite direction. So therefore we have that the third elementary row operation, its elementary matrix, EI alpha j, has an inverse called EI minus alpha j. So that's the third lemma, done. Every elementary row operation is reversible, therefore every elementary matrix EI has an inverse. and we've calculated them exactly so that you can use those. All those, now we have those three lemmas for what purpose? Well, to prove this theorem. Down here in the bottom corner of the board, some things never change. Bottom right-hand corner of the board is always the most important one, right? Anyway, so now the proof of the big assertion. If, and you can't see that, if, here's the big assertion, why Gaussian elimination works. If AX equal to B has a solution set S, right? So that's filled with a bunch of vectors, X's, that if you put them in here, make that equation true, right? Definition of solution set. If AX equal to B has solution set S, while A prime X equal to B prime has solution set S prime, where the augmented matrix AB is row equivalent to A prime B prime, what we're going to show is therefore those two solution sets are exactly the same. So that's why we do Gaussian elimination, because usually that product, that output from Gaussian elimination, that row reduced echelon form that RREF gives you so easily, that one, the solution is easy to pick off from that, right? And now we're guaranteed it solves the original system of equations, original matrix equation, original vector equation, all those. So how does the proof work? Using those three lemmas. Well, it goes like this. Here's a way of proving two sets are equal. We're trying to prove that, get the shadow off of there. We're trying to prove that the solution set for the first one is the same thing as the solution set of the last after Gaussian elimination. Okay, a way of showing two sets are equal is to show that one is a subset of the other and the other is also a subset of the first, right? So you have inclusion in both directions. So let's show this one. Suppose X is in the regular solution set of AX equal to B. Well, then the statement AX equal to B is true. Okay? If I multiply both sides by E1, I also get a true statement. That's lemma 1. Keep doing that. Keep doing that. Let's say there are S elementary row operations that do Gaussian elimination on that system. That can be represented by this product being equal to this product. What allows me to say that? Lemma 2. What was lemma 2? Just to remind you. Lemma 2 was this one. Every elementary row operation on the augmented matrix A, B is equivalent to multiplying AX equal to B by an elementary matrix EI on the left. Okay, so that lets me say that, look, I've got these two things are row equivalent. Lemma 2 applied over and over again is what allows me to say, therefore, AX equal to B, after you multiply by S of these matrices on both sides on the left, gives you A prime X equals to B. That they are row equivalent is the same thing as saying we can go from this product to this product to this product and get to this one. So we haven't changed x here. That same x that belonged to S is now in this, which is also a true equation by lemma 1. Therefore, this x also belongs to S prime, the solution set of this other system. Okay, now let's reverse it. Let's show that if you start with something in S prime, that you're going to show that that same x belongs to S. All right, so suppose x belongs to S prime. That means A prime x is equal to B prime by definition of S prime. By lemma 2 again, I can rewrite A prime as this product of elementary matrices times A, and B prime as this product of elementary matrices times B. Multiplying on the left now by ES inverse, and then ES minus 1 inverse, and then ES minus 2 inverse, and so on for a finite number of steps until you're left with AX equal to B, as also being a true statement. So X belongs to the solution set of AX equal to B. So therefore we have S is equal to S prime, and we're done. Gaussian elimination works as long as you follow the rules of Gaussian elimination. Use equivalent row operations, finite number of them. And so the RREF button and the REF button work and help us say the solution sets are exactly the same.